Hey guys, welcome to the last video lesson for calculus. This one's going to be on the fundamental derivative rules. Watch this one prior to the class for Wednesday. So in the previous lesson, we learned about the idea of instantaneous slopes, that is tangent lines on a curve. We can consider how fast the curve is changing at a point, right? As opposed to having slope be only about lines, we figured out a way that we could make it make sense on a curve. How fast, what direction does the curve have there? And what's more, we learned about the derivative, a function that describes how another function is changing, that is, the slope of that first function. So that derivative would be f prime, right? If we've got f of x, then f prime, f with a tick mark after it, is the derivative. And the great thing about f prime is it tells us that instantaneous slope for f of x, our normal function, by just plugging in the location into f prime. So for example, if we want to know the location at a, if we want to know the slope at a, we just plug in the location of a into f prime. So f prime of a is the slope, the instantaneous slope at the location a on our curve. Same thing, if we want to know the instantaneous slope at b, it's simply f prime of b. So the derivative is pretty darn great. We figured out how we could find instantaneous slope and the derivative by combining the difference quotient with limits. This gave us the following two definitions. We had the instantaneous slope at x equals a, if we only wanted to know what the slope was at one location a, and that was the limit as h goes to 0 of f of a plus h minus f of a all over h. And then there was our derivative definition, and the derivative was very much like instantaneous slope, except instead of using an actual location value, it left it as the variable x, so we'd wind up getting a useful formula at the end. It was the limit as h goes to 0 of f of x plus h minus f of x all over h. The problem is that these aren't very fast or easy to use. I mean, sure, we could find the derivative of something like f of x equals x squared minus 3x, like we did in the last lesson and like you worked on that worksheet. But what if we were up against a monster like this? I mean, look at g of x. That would be awful to use this limit process on, right? Could you imagine trying to find g prime from that limit process? It would take forever. Good news, it turns out that there are actually a wide variety of rules that allow us to easily and speedily find the derivative for the vast majority of functions. In this lesson, we'll start to look at what those rules are and how we use them to find derivatives. So you might be asking, where do the rules come from? And that would be a great question. Sadly, we don't really have time in this course to actually show how you manage to discover these rules or prove that they're true. All these rules somehow stem from that formal derivative definition of the limit. The formal derivative definition, that was the one that used the limit h goes to 0. And given enough time, if you were working with that formal derivative definition, you'd start to notice these patterns regularly showing up. And eventually, you could even prove those patterns so that those patterns always have to happen by looking at how that formal definition works in really specific ways. But for this class, you're just going to have to take my word that the upcoming rules are legit. I'm not lying to you. We just sadly don't have time to really explore the deep reasons why we can always trust that these are working. But these will always work, assuming you follow them. All right, so our first rule is the power rule. This one says that if a function is simply a constant exponent on a variable, the derivative is very easy to find. All you do is you place a copy of the exponent in front, and then you subtract 1 from the exponent. And so, once again, saying it out, we've got that if given that n is a constant number and we've got f of x equals x to the n, then the derivative, f prime, is going to be n times x to the n minus 1. And I want to point out again, n has to be a constant number. This doesn't work if that exponent is not a constant value. It actually has to be a constant value. If it's something else, this winds up breaking down. All right, let's see some quick examples. So first off, what if we've got f of x equals x squared? So what we do is we take the 2, the exponent, we move it to the front, and then we reduce that exponent by 1. Subtract 1 from the exponent, so it's 2 times x to the 1 at this point, right? 2 minus 1 is 1. And so we could simplify that to just 2x. Move on to g of x equals x to the 8th, exact same thing. We move the 8 out to the front, and x to the 7, right? Subtract 1, that's our new exponent. Same thing even for a big exponent like h of x, 1017 x to the 1016, right? Just move it down and subtract 1. Simple as that. So the amazing thing about the power rule is that we can even work it in some strange situations, right? Things where it doesn't seem like it's x to the n. So starting off, look at a of x equals x. At first, we don't see an exponent on it, but we remember, oh right, what it is there's only one of them, so we could rewrite that as x to the 1. Now that we see that it's x to the 1, we could apply this. So we move the 1 to the front, x to the 0 now. Well, what's anything raised to the 0? 1, so it simplifies out to just 1. And this is a really good thing to remember in specific if you've just got a a variable on its own, right? No exponent, just the variable sitting there. Then when you take the derivative of that variable, it just winds up disappearing and turning into a 1. It just goes away and turns into a 1, which is pretty common. You're going to see that showing up a lot in a certain way. All right, b of x equals 1 over x to the 4th. Well, once again, we don't have a direct follow of x to the n, right? It's got an x to the 4, but it's on the bottom of a fraction. But because it's on the bottom of a fraction, we could flip it to the top as x to the negative 4, right? X to the negative 4, no longer in a fraction, so we're now following that structure of the power rule. So we bring down the negative 4 and we subtract 1. Notice that we're not reducing the value to negative 3, we're actually subtracting 1. Negative 4 times x to the negative 5, and alternatively, you could also write that as negative 4 divided by x to the 5. Which one's going to be more useful to you will depend on the context of what's going on, right? If you had to multiply that against other things afterwards for some reason, right, it might be more useful to leave it as x to the negative 5, so maybe you'll have those exponents cancel out. But if you actually needed to compute it, it might be more useful to have as negative 4 over x to the 5, right? Depends on the situation. Finally, c of x equals cube root of x. Well, cube roots we can actually rewrite as 1 over 3 for an exponent. So we've got x to the 1 over 3. At this point, we can pull down the 1 over 3, subtract 1 from a third. That gets us negative 2/3. So we've got 1/3 times x to the negative 2/3. And once again, it might be more useful to write it as 1 over 3x to the 2/3, right? Our x is flipping down into the denominator, but it also might be more useful to write it just in the simple way it came out directly, 1/3 x to the negative 2/3. Depends on the situation. All right, the thing that I want you to take away is that, in short, if things look complicated, your first instinct should always be, how can I rewrite this as a simple exponent? Now, as we get farther into things, you're going to start to see cases where you can't just rewrite it as a simple exponent, but it should always be your first instinct. Is there a way to just rewrite this as a simple exponent? Because if it's a simple exponent, we use the power rule, really easy to use. So it's great anytime you can put something in a format where you can apply the power rule. So always think first, how could this be an exponent? All right, we're ready for our next rule, constant rule. This one's super simple. It says that if a function's just a constant number, then its derivative is 0. Simple as that. So if f of x equals c and c is a constant number, then f prime of x equals 0. So if we've got f of x equals 4, g of x equals negative 18 squared, h of x equals 17,864 times root 23, it doesn't matter. The derivative of all of these is 0, right? It doesn't matter how big the number is. It doesn't matter what's going on to the number. If it's just a constant, it turns into a 0 when you take the derivative. And that makes a lot of sense, right? A constant function is just a flat line. What's the slope of a flat line? 0. Next rule is the multiple rule. This one says that if a function is multiplied by a constant, then the derivative is just that constant times the function's normal derivative. So written a little bit more formally, if we have c being a constant and f of x has some derivative f prime of x, then if we create a new function g of x that's c times f of x, the derivative of g is going to be g prime, and that's just c times f prime of x. So basically, our constant just sits there and doesn't do anything, while the part that is a function-y thing can actually take the function and, take the derivative, and we get a nice normal derivative. It's a little bit easier to see as an example, so let's check those out. F of x equals 5x cubed. First thing we could do is we identify, oh, that's 5 times x cubed. X cubed, we've got a rule for, right? We use the power rule, so we can pull down that. So we have 3x squared for that. The 5, nothing happens to the 5. It's the constant. It just sort of moseys on to the next part. It doesn't actually do anything in the derivative. It just sort of goes from the first function to the derivative function, right? It just moves through. So 5 times 3x squared, at this point we simplify, and so we get that f prime is 15x squared. We do the exact same thing for g of x. We separate out, we see it's negative 8 times x to the 11th. At this point, we can take the derivative of x to the 11th, so we get 11x to the 10th. We have to keep that negative 8 sticking around, and don't miss that negative sign. It was negative 8 multiplied, so it's negative 8 times 11x to the 10th. We simplify negative 88x to the 10th for g prime. Finally, h of x, we can split that into 92 times x to the 1. As we saw a little bit ago, the derivative of x to the 1 is just 1, right? 1x to the 0, so it just disappears into a 1. 92 times 1 simplifies to a simple 92. You remember a few moments ago I said if it's just a variable on its own, it kind of disappears into a 1. That was why I was specifically using the word disappear, because it often, if it has a constant in front of it, it just disappears entirely, and all you're left with is the constant, right? We had 92x in our initial function h, but when we took the derivative and got h prime, we were only left with 92. The variable, because it was just a variable on its own, sort of stripped away. right? The important thing is to realize that the multiple rule has to be based around a constant. It works great for c times function, but if it's two different functions where each piece can change, it's not constants being a constant being multiplied on something that's changing around, like f of x times g of x, then it doesn't work. The derivative of f of x times g of x is not f prime of x times g prime of x, right? If you can separate into two different pieces, you don't just take the derivative of those two pieces. You have to make sure one of them is actually a constant. So, for example, if we had capital R of x equals x cubed times x to the seventh, we couldn't just say, oh, that's 3x squared times 7x to the sixth. That doesn't work. We can't separate it as multiples and go, oh, we can take the derivative of each one separately. No, it only works with a constant. What we have to do instead is combine them into one thing. X cubed times x to the seventh is x to the 10th. So now we can apply the power rule. Derivative of that, we get 10x to the 9th. All right, our last rule is the sum rule, and this says that if a function is made up of smaller functions just being added together or subtracted, then the whole derivative is just combining all those derivative pieces in the same way. So given that we have some g of x and h of x with their derivatives g prime and h prime, then if f of x is just built out of them by adding them together, right? F is g plus h, then the derivative of f is going to be f prime being g prime plus h prime, right? We're made up of two different pieces added together, so when we take the derivative of it, those two different pieces take the derivative separately and then just get added back together at the end. We can see this more clearly a little bit with some examples. So say we've got d of x equals x to the seventh plus x cubed. Then what we see is we've got two separate things based around a plus sign, x to the seventh plus x cubed. That means we can take the derivative of those separately. So x to the seventh is 7x to the sixth, x cubed is 3x squared, so the derivative of everything is 7x to the sixth plus 3x squared. We're taking the derivative of each piece on its own and then just keeping them added together. Same goes for e of x. Over here we've got x to the 12th minus x to the 6th. They're being separated. This time it's not addition, but the rule holds for subtraction as well. X to the 12th minus x to the 6th. We can do the derivative on each piece, so we get 12x to the 11th minus 6x to the 5th. Great. The wonderful thing about all these rules is that they can be used together, right? If we've got all these rules, we don't have to use them separately, we can use them in concert. So now a monster function like that one we saw at the start is actually super easy to handle, right? G of x equals x to the 5th minus 17x squared plus square root of x minus 1 over x to the 5th looked really scary when we were going to have to approach it with limits, but now we can just break it up into bite-sized pieces and use these rules. The only problem right here is square root of x and 1 over x to the 5th aren't really in that nice power rule structure, right? We don't have x to the number, but we can change that, right? Root x becomes x to the half, and 1 over x to the 5th becomes x to the negative 5. At this point, it's really easy to apply the power rule, and the 17x squared is just the power rule with the constant multiple rule. We take the derivative of all those, and derivative of x to the 5th is 5x to the 4th minus, right, because we separate based on the sum rule, we keep them separate, so 5x to the 4th minus 17 2x, right, just the derivative on x squared multiplied by the constant it had, plus 1/2 x to the negative 1/2, just bringing down the 1/2 and then subtracting 1 from the exponent, and then minus quantity, negative 5 times x to the negative 6, just bringing down our exponent, subtracting 1 once again. At this point, we can do a little bit of simplification, so we get 5x to the 4th minus 34x plus 1/2 x to the negative 1/2 plus 5x to the negative 6. Done, and that's our derivative. We could rewrite it if we wanted, moving those negative exponents into the bottom and bringing that 1/2 exponent into a square root format, but they're both perfectly reasonable ways to answer that. All right, at this point we know pretty much all of our rules, so now that we know how to find the derivatives, let's go over some of the language that's associated with them. First off, we call this process of obtaining the derivative from a function differentiation. That's the name for this process. If we want to apply it as a verb, we say to differentiate, right? So if we want to find what the derivative of f of x is, we would differentiate f of x to get f prime. The process of doing that differentiation is called differentiation. You kind of heard it when I said it there. All right, next, if we want to talk about a function having a derivative at some specific location, if the function has a derivative, has an instantaneous slope at some location a, then we say f of x is differentiable at a. If we're able to do this derivative process at every single location, if the differentiation works everywhere we could possibly go with the function, then we say it is differentiable everywhere. Or, depending on the context, we might simply call it a differentiable function. Let's talk a little bit notation now. So functions aren't the only thing we can differentiate. While we haven't mentioned it so far, you can also differentiate equations. And this kind of makes sense because functions and equations are really similar for graphing, so it's not a big surprise that we can differentiate equations. Now, the way that we show that an equation has been differentiated is we can use prime notation, those tick marks, a little tick mark after it, f prime, etc. They can be used to show the derivative of an equation, but it's less common. The more common thing is this d blank over d blank notation. And we'll get into what that means a little bit more. We'll explain it here, and we'll get a better understanding of why this notation exists in the coming weeks. So if we've got something like y equals x squared, then when we take the derivative, we could call the derivative either y prime, or we could call it dy over dx, right? See this d blank over d blank? In this case, dy over dx, because our output variable is the y and our input variable is the x. So dy over dx would be a reasonable way to do this, although it wouldn't be that surprising to see something where it said y prime for the derivative. So we can use this d blank over d blank notation to indicate derivatives for functions as well, but we usually use prime notation. So going over all the notation we've seen, if we're taking the derivative of function f of x, it's really common to see f prime, that little tick mark after it, to show the derivative. You could see df over dx, but that would be fairly uncommon, but not unheard of. You would definitely see it from time to time, but not a lot. On the other hand, if we're dealing with an equation like y equals blah, 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 then if we take the derivative of that, your most likely thing that you're going to see is dy over dx to show that you're talking about the derivative of y. Although you could also see y prime. It's less common, but it is more likely to see y prime than you are to see df over dx. We could also use d over dx, that d over dx, to indicate differentiate this, the derivative of this expression, basically saying we're going to do differentiation to this thing that comes after the d over dx. So d over dx f of x says the derivative of f of x, or differentiate f of x. d over dx y says the derivative of y, or differentiate y, right? Or we're considering the derivative of y. We could do the exact same thing with an actual expression, d over dx 3x to the 8th. We just take the derivative of 3x to the 8th, right? We've got all these great rules, so we can apply it like an operator and do this thing to it. So 3x to the 8th comes down, 3 times 8, 24, and we subtract 1 from the exponent, so we get 24x to the 7th. Finally, it's important to note that this sort of d over dx notation is based on the variable involved. If the input variable is different than x, we swap out for the symbol that is a variable. We refer to the variable involved in the differentiation by saying that we're differentiating with respect to that variable, right? So if the variable involved is x, we say we're differentiating with respect to x. So if we had something like s equals t squared minus 3t, and we took the derivative of that, we'd get ds over dt equals 2t minus 3, right? Because our output variable is the s, and our input variable that's able to move around is the t, so output on top, ds over input on the bottom, dt, ds over dt. We differentiated that equation with respect to t. We'd have the exact same thing over here, d over dz of 4z squared plus 7. That's saying differentiate this expression with respect to z, which is important because the variable involved is z, so we have to be differentiating with respect to z. So the derivative of that would be just 8z. Great. All these new rules are wonderful, but the thing that really matters is what a derivative is about. And here's the heart of the derivative. This is the thing I want you to take away from this course most of all, is the derivative is a way to find instantaneous slope. By plugging a location into the derivative, we get the slope at that location. That's what the derivative is about. So a lot of calculus classes are going to focus on the nuts and bolts of finding derivative. There's a lot of stuff to talk about how do you actually get the derivative out of it. But don't let those fancy rules distract you from the thing that matters the most. No matter how many rules you learn, no matter how you know how to take the derivative is about one essential thing: slope. Being able to talk about that instantaneous slope on the curve. That's why we talk about the derivative. Because the derivative is about finding slope at a location, that means it can actually not exist. So the derivative is not something you can rely on 100% of the time. Sometimes you're going to see exceptions, locations where it is not differentiable. So for example, consider f of x equals 1 over x, which we've got the graph of here. What would be the slope at x equals 0? Well, we look at it and it's just not there, right? And that's exactly it. Since the function doesn't exist at x equals 0, we can't say that it has a slope at that place. So f of x is not differentiable at x equals 0. doesn't exist there. It doesn't make sense to say it has a slope. We could also see this if we were to work through the derivative, right? We could rewrite f of x as x to the negative 1, which allows us to easily take the derivative. Negative 1 comes down, so we get negative x to the negative 2, which we could rewrite as negative 1 over x squared. So there's our derivative, negative 1 over x squared. But if we were to try to plug in the location of 0, we'd get negative 1 over 0 squared. We're dividing by 0, so it does not exist. So we also see that the derivative is also helping cover us here. The derivative is showing, hey, that just doesn't work. It doesn't make sense to go to that place. You can't say that it has a slope there. But we can also see that from the graph. It's just, there's no slope. It doesn't exist, and what would it mean to have a slope at that place? We can even have this when the function does exist and is continuous. Consider f of x equals the absolute value of x minus 2, which we've got the graph of here. What would be the slope at x equals 2? This one we might be a little bit more tempted to say that there is something there, but you look at it for a while and you start to realize, there's no instantaneous slope because it's got this sharp corner, right? Before the 2, it's marching at this very clear negative 1, negative 1, negative 1 slope. Right after that corner, it's marching at this very clear positive 1, positive 1, positive 1 slope. But between those, that moment at the 2 where it suddenly shifts, it does this sudden turn. We can't name a direction. The function isn't moving in one direction at that place. It's kind of caught between two different directions. And because of that, it just doesn't make sense to say that the function has a slope at x equals 2, so it's not differentiable at 2. Great. That wraps it up for this lesson. Thanks for watching the videos, and I'll see you in a little while. Have a good break week when it comes time for that. All right. Bye, guys.